Hear me? Yeah, so firstly, super happy to be here. It's been like, some time since the pandemic, and I'm just really excited to be able to give a tech talk again and meet all of you guys. I think there are many new faces in the community as well as many familiar ones, and it's really, really cool. So today I'm going to be talking about, I'm going to be talking about end-to-end encryption on FormSG. But before I do so, I just want to give a quick intro to myself. My name's Yuan, or Yuanruo. You can look me up on LinkedIn or after the talk. I'm an engineering manager at OGP. I wonder how many of you have heard of us open government products? Yeah, awesome. Okay, so that's about half the team. Thanks, Michael. For those of you who don't know, we're an experimental unit, like Sarah said, mostly made up of engineers, designers, and product managers. And what we want to do and achieve in Singapore is to adapt the best private sector and tech company practices to build technology for the public good. And like all of you, live in Singapore or have been in Singapore, and one thing you have to do in Singapore is you have to transact with the government and use government services. So here's like a huge laundry list of all the services that my team of about 100 people have built over the years. Today I'll be talking about FormSG, which is the logo in the top left. But we also have a whole slew of other services, including like mc.gov. When you go to the polyclinic, you get a digital MC. RedeemSG, which is the preferred way for the government to put $100 in your pocket when the budget comes or when the election comes, right? Scam Shield, which is using like on-device machine learning to filter out scams, vaccinations. If you got your jabs in Singapore, you would have booked your appointment through our systems, and many, many more. But today I wanted to talk about Forms. Forms is one of our biggest and most successful products in Singapore. It's been around for about 4 years, and throughout this time, we've actually gotten more than 171 million submissions. As a government, of course, or in the public service, we're collecting like all of this data, from Singaporean citizens and foreigners. And of course, what's really key is how can we protect this data, because this data does not belong to us; it belongs to all of you, right? And although this product, the moment we wanted to make this product go up and hit scale, what we needed to really do is to make sure that, if ever there was a data breach, right, that all your data would always be safe, right? Your security and your data safety comes first, right? And the way we decided to do that is to use end-to-end encryption. So just to give a bit of context to how the product scaled up, right? Because the Singapore government, we pride ourselves as being super efficient, but the reality was that the pandemic really forced 200,000 public servants to truly become digital. So what I mean was, during the pandemic, when we were starting the Forms project, for about 2 years, we collected 3 million responses, right? And after the pandemic, you can see there was this huge acceleration, this huge trend, where basically the public service had to digitize overnight. And all of you, when you were applying for grants, applying for various services with the government, all of that moved to FormSG overnight. What we saw in our data that during the pandemic was that from 3 million responses over 2 years, we went to collecting 3 million responses per week, right? And effectively, we 100x our scale the moment the government announced circuit breaker. Because just like all of you, public servants have to work from home too, and then they needed a way to collect data, and it's not going to be Google Forms, right? It's going to be the official platform. Right, and now that we're sort of in steady state, we're collecting about 1.5 million responses per week. And for a country of 5 million people, this is a huge deal for us. So FormSG, it's kind of, I like to explain it as Google Forms on steroids, because it's actually super, super featureful. Got a whole load of form fields available, and which is you can kind of see on the left. But really, what's really interesting on Forms is that we don't actually store any of your data in plain text ever, right? Zero knowledge, essentially what that means, right? Or end-to-end encryption, what that really means is that when a public officer creates a form, they receive actually a cryptographic private key that is actually never seen by backend servers, and therefore never seen by system administrators. And so all of these submissions, they're encrypted in your browser before being submitted to the cloud, right? We use AWS, but it doesn't matter. Like, we are the system admins, but we have absolutely no idea what is being encrypted. And when the public officer accesses your data, because you applied for something, they actually provide that cryptographic key and then decrypts that data on the other end of the browser. And this is extremely challenging to implement, which is why we have a talk for it. But let me just step you through like what the UI looks like. So this is when the public officer, they create a new form, they give it a name, and they actually get to choose like two modes of how they want to receive responses. So the old way was an email, right? So you fill in a form as a citizen, our server send an email, and then we never store the data. It's like in secured email service. But then as our use cases got larger and larger and got to national scale, right? It's not just like maybe 100 responses for like a public event, right? It's not like going down to your CC for like, I don't know, like line dancing or something. It can be very large, like hundreds of thousands of responses. We started to realize, okay, we actually needed a way to store this data and help our users, help our public officers like manage this data. So we have FormSG, the FormSG mode, or storage mode as we call it. And our public officers, they're not like cryptographically trained, they're not cybersecurity trained, they're not techies. So we tell them, okay, please download this form password, and if you ever lose it, you will never be able to get the data back. So like, please store it super securely. And this is actually the private key to all the data that they encrypted. And so yeah, they go ahead, build the forms as usual, and when it's time to decrypt the responses, they supply the private key, right? And there's like an upload function where they just upload the key file. And this is kind of what it looks like in the back when, let's say, you have about 20,000 responses, they'll be listed out in a table. But it turns out that implementing the export CSV feature, turned out to be extremely challenging. Like, from a user perspective, this looks deceptively simple. Like, yeah, download the CSV, right? It's a file of text. Like, what could go wrong? Right? It turns out that because end-to-end encryption, because cryptography can be expensive, when you scale it up to hundreds of thousands of submissions, that it really pushes the bounds of browser performance in terms of memory, in terms of CPU, in terms of even like device setup. And it can take a really long time to actually download all the responses. If your device was a bit older, a bit smaller, maybe it's mobile, then you actually get these like crashes and even battery life drain. So it was like terrible UX, and we had to like figure out how to fix all of that. So I'm going to share, like, for the rest of this talk, what goes on under the hood, right? So the first time we designed this in about 2019, we were thinking, okay, how can we build this feature? What does end-to-end encryption look like? So it's usually implemented as an envelope encryption scheme where you use public key cryptography such as RSA, right, to mediate a key exchange. And then once you have that key exchange, you can then use a symmetric key such as AES to implement. Now the challenge was that it actually took 2 hours and 40 minutes on 100,000 like form submission records, and each submission record was like really, really slow because you had to do this key exchange like 100,000 times, and this was unacceptably slow. We're going to add a lot of latency to what the government is, which is like a big bureaucratic machine. So we're just going to add so much latency, and we couldn't push that out. And so we looked across the cryptographic landscape, and we figured out that, okay, if RSA is so slow, what are the alternatives? And it turns out elliptic curve cryptography was the answer, right? If you look at the table on the right, the US government, the NIST standards actually did a comparison and says that the comparable key length of elliptic curve cryptography is on par with symmetric curve cryptography. So that's to say, when you switch to an ECC cryptographic scheme, the amount of compute, the amount of cryptographic operations you have to do, right, is far lower than compared to RSA. You're like talking about like an order of magnitude. So this was going to be our preferred approach, where we could, pick much smaller key sizes for equivalent security and reduce the computational requirements. And this is supposed to go like much faster. So we tried it out. We built. This is all implemented in the web browser, right? Where essentially what happens is 2 steps, right? After the public officer like uploads the secret key, the browser the cryptographic operations is a split between a Diffie-Hellman key exchange, where you mediate a public-private key pair, and then the stream cipher. And one part, like I said, was really slow, right? And if it was RSA, it would be much slower. But when you switch to Diffie-Hellman key exchange with elliptic curves, it was a lot faster. And the stream cipher, which is something called XL20, it's not super important, but that always runs very quickly. So what we did was that we switched our implementation in the prototype, and the same amount of data went from 2 hours and 40 minutes down to 8 minutes. And yeah, so we thought, okay, this is great, right? So could we get it to go even faster? Now the issue with JavaScript, of course, is that it's single-threaded, which means that anything you run on the main thread blocks all of your rendering, it blocks all of your user interactions, right? And so we had to actually, although it worked in theory, we had to offload it to a web worker. And actually, when we did that, it went down to 2 minutes and 30 seconds. And of course, when you use one web worker, then the next question is, why don't you use more, right? So we scaled up our web workers. We actually used the window.navigator.hardware concurrency variable to detect how many web workers or how many threads your web browser could support, and we'll always pick that number to make sure that we maximize the parallelism out of this implementation. So that actually brought down the total duration to 45 seconds. And so at this point we thought, okay, this is great. We can launch for a nationwide use case. So I don't know how many of you guys remember like this bicentennial notes thing where basically we all pat ourselves on the back and said, okay, we made it to 200 years after Sir Stafford Raffles like landed in Singapore. And we had like this big national use case to support. And we thought it was going to go off without a hitch, right? And when we look at the form, it says, okay, it looks like a simple form with 6 questions. Until we actually got our users to call us and say, hey, we can't access our data. We only have 120,000 submissions, but our browser's crashing. So what on earth is going on, right? So it turns out that because FormSG has this like complicated like logic structure where the form builders wanted to make sure that you don't get overwhelmed by the number of bank branches you could go to pick up your bicentennial notes. They implemented this 50 form fields, right? Where if you selected which region of Singapore you lived in, and then you selected which bank, and then the relevant bank branches would show up. So in theory, although from the user perspective, it looks like only 6 form fields in the form, in theory there were 50 because of all the bank branches in Singapore and all the like the tree branching logic that went into like building like a good user experience. And so that meant that we actually had to like deal with like high volume and also really big forms all at once. So we actually had to do this like debug and fix all this in like 3 days so that we didn't like crash a nationwide campaign. And yeah, so this is what I was talking about. Like there were over 50 fields that were hidden by form logic. So we had to like massively improve decryption performance in like half a week. And so what we started doing was actually performance profiling. So we actually observed that there were kind of 2 main areas that we had to fix. First was the sawtooth memory spikes that were causing runtime crashes. So this stuff is in like Chrome like profiling tools. You can go to performance and like just record the performance of the application and do a playback, and you can see this. So yeah, apart from the sawtooth memory spikes, we also saw like our web workers idling for long periods of time. So all the blank areas is where actually our web workers are not doing any work. So that looks a bit suspicious. So the first thing we looked at is our implementation, and we said, okay, the garbage collection pressure was too high. So how can we, improve the memory footprint that our application was taking? Well, it turns out that the garbage collection pressure was traced to a stream parser library called obo.js. We tried to be like extra smart. We tried to decrypt the moment like the network stream came in and not wait for the entire network stream, not wait for the entire like JSON load to land in the data before we started decrypting, because that was how soon we wanted to decrypt, and that turned out to be quite challenging because stream parsing itself requires a lot of like, string operations are expensive from a CPU cycle point of view, and we were using quite an inefficient library. So our trick was we were just going to return a new line delimited JSON instead. So it's not actual proper JSON, but it just means that you send multiple JSON records, not in the form of an array, but in the form without the array boxes, right? And that actually turned out to reduce our memory footprint by about 10 to 20x, right? And we also fixed like some various like code flaws that we had. So for example, one of the frequent causes of the memory spike was we tried to do this like array string concatenation because we didn't pay attention to what the blob API actually was. So when you have a blob, it turns out that the blob constructor takes an array of whatever it might be, but the point being that it holds pointers to all the data. You don't have to concatenate it to put it in a blob. So by a more careful reading of the web API, we managed to like simply reference the existing data and not actually build up this like single huge object in memory, right? This string in memory. Yeah. And then we started looking at the thread profiling, and it looks really weird. Like if you ever see this really strange performance profile where you think your code is supposed to parallelize something and it turns out to be just like this staccato patches, you should be concerned because that's not parallelization. That's just that just looks like random execution. And it turns out that we had a bug in our round robin scheduling where we were not distributing. We were distributing the work, right, of decrypting each payload, not at a point when it first received, but at a point where the worker had completed it. So essentially our round robin, this like, and by round robin algorithm, I really mean like a modulo, that's computing the modulo. Even something that simple had a bug, and after fixing it, we saw that actually there were like clear areas of parallelism now where all the web workers were executing before handing back execution to the main thread, and then there was this like back and forth where you had clear blocks of parallelism and then clear blocks where they're not doing anything. So this was also a bit strange. We were like thinking, why is there such a long wait time of I think it was about at least 100 milliseconds between the workers executing and then the workers idling. So what was going on here, right? And it turns out that for every 15 milliseconds we spent decrypting, 266 milliseconds were spent parsing and like performing various stream transformations. And so how do we fix that? Why was it so long? It turns out that when you encrypt data, and it can be represented in a base 64 string, which can be represented in ASCII, but the library was catering the UTF-8. So it made the parsing extremely expensive. So what we did was we did like what any good software engineer would. We copied, pasted the code into our own repo, and then we tore out all the unnecessary features. We just made sure that we simply cater for ASCII parsing, and that actually like incredibly like sped up our decryption down to 13 seconds. And I mean the test case is 13 seconds, but the amount of time spent in main thread we actually reduced from 266 milliseconds to 35 milliseconds. And after we did all this, which was like in a span of just a couple of days, and it was like the most stressful days on the team, our users showed up and they were like, hey, we want to get access to our data now. Can I use this thing to download my data? And all of us, we are probably on like really high performing laptops and MacBooks and so on. It turns out, this is the public service and the government, and they have to wait for their like periodic tech refresh. So they were still running on Windows 7, Internet Explorer, like 4 GB RAM. But it went off without a hitch. We actually got this technology to work on that old device. So that was like sweat off the brow, right? Yeah. So thank you. Yeah. So long story short, like we did a whole bunch of engineering optimizations, and we tried a lot of things. But this is just like the overall summary of all the improvements that went into making FormSG great, right? So from the performance optimization point of view, all of these improvements actually went into a 33x speed up and a 10 to 20x smaller memory footprint. And compared to our very first prototype, it was actually 600 times faster compared to RSA. Yeah. So always go elliptic curve if you can, and if you're building a high performance end-to-end encryption for whatever system you're building. Right. Yeah, we also had like a whole ton of learning points that I thought it'd be really cool to share because this is like, it was learned from like sweat, blood, and tears. Yeah, so here's a chart that basically shows you the marginal performance improvement versus input effort. And essentially what the main takeaway I wanted to share with you guys is to avoid premature optimization whenever you're building something. So the very first switch we made from RSA to ECC actually gave us huge amounts of performance improvements, but every subsequent improvement we made was at ever increasing cost, increasing expertise, and now we actually have to maintain this code, right? And so I just wanted to share that this was extremely obvious that to us that if we had a chance, if we didn't have to do like all of these optimizations, we wouldn't. And it was only driven by necessity. So don't over-engineer, don't prematurely optimize. The second thing is like when it comes to performance bugs, like never speculate, just performance profile because you never know what the issue could be. So these are like all the things like we discussed internally on our team to try and make the app go faster. Like not all of them make sense. So for example, like some of them do sound on the surface like it makes sense. Like say we need WebAssembly, but when we looked at published benchmark, like actually it was going to be the same speed as the high performance cryptographic JavaScript library that we were already using, right? Someone suggested that hey, maybe we need to look at the performance of string appends. That didn't turn out to help. Someone suggested we can pre-allocate arrays by just calling array.fill. Like that's not how memory allocation works. And certain things that that seem to make sense, like moving embarrassing parallelization into your web workers instead of on the main thread. Like it seemed to make sense, but it turns out only you achieve only like marginal performance gains. So yeah, always performance profile. So yeah, actually that was all the engineering work that we did. I just wanted to say this has been rolled out and it's been stable in production for a couple of years now. But we're always excited to share this story from the Forms team and from OGP. We are open source, so if any one of you are excited by this sort of work, come and look at our repo, come and look at the issues that we're tackling. Most of our products at OGP is actually open source. So yeah, just feel free to come visit us. And if there's any one of projects that excite you, we'll be very happy to get your help and support or input, right? And lastly, this is the current team that's working on this and making it all possible. We're actually working on a big front-end migration. So you guys are going to get like a great UX improvement soon. When that happens, I'm sure you guys will see it, and I'll let the team share more about that in the future. But thank you very much.
Do we have any questions? While we do questions, we will head into our raffles giveaways. So who can guess? Maybe Ben, if you're ready, I can get you on stage. Any questions before we get the Star Wars Lego out? Yes, very nice.
Hello.
Hi.
What about the subtle crypto APIs? Have you all considered that?
So the subtle crypto is it a native web crypto?
Yes, it's a native web crypto API.
Right. So I think back in the day we were looking at that as a possible option. I don't believe it was completely supported on all the browsers. So which meant that we had to have a JavaScript implementation instead of a native implementation. But if we didn't have to support Internet Explorer back in 2019, that would definitely have been on the cards. Yeah.
Yeah, thanks.
Sounds like a good experiment. Someone can contribute on a feature branch since it's open source. All right. In that case, Ben. Well, first of all, thanks, Yuanruo. Thanks so much. And